Good morning, everyone, and welcome to Physics 131. We're on to class 33. The weather in Toronto is frightful, sort of a combination of rain and snow where I am. More rain, really, but it's kind of cold. So let's share my screen 2 here. Share screen 2. And then I'm going to talk about what's on the agenda. So this was that field of wheat that I was telling you about last time. So when a wave travels from place to place, the wave can travel very, very far, but the particles which actually make up the wave only will oscillate in place. And you can sort of see these the waves moving a long distance over a wind, I guess, moving over a field, but the grass itself just sort of stays in place. It's a good thing to keep in mind. We're going to talk about wave intensity and this new way of measuring intensity with a logarithmic scale called the decibel system. So we call it sound intensity level. And then I'll talk a little bit about superposing waves, and that's pretty much it. So what I want to do first is see if we can do a snap filter thing. First of all, we have to choose the filter. So see if you want to vote for any of those. And then we'll see if we can make it happen on Snap. Chat window. Okay. Someone said the fire is so delightful this year. That's true. And Haley, I will record Thursday's session for sure if you can't make it. Yeah, I was looking at this, my twin. It looks pretty good. Actually looks a lot like my sister, to tell you the truth. Yeah, I only just installed Snap today. So it's looking like, let me just give you another 5 seconds to vote in. 4, 3, 2, 1. And the share results, it looks like 40% voted for this anime style. So let's try to make it happen, shall we? If I go on to Snap Camera, there we go. Okay, so I'm your new prof. Okay, see if that holds up. I'm going to do another poll. This is about 2 wave pulses traveling along the same stretched string, one after the other. You can see something is different about these 2. So how would you compare the speeds of these 2 waves? So I'm going to launch another poll. Is it that pulse A goes faster than pulse B, or does pulse B go faster than pulse A, do you think? Or they're the same, or there's not enough information to tell? Okay. Can't see my teeth in this thing. I'm just playing with the filter. All right. Okay, so let's end this polling. See what the survey says here. Give me another 5 seconds to make a choice. Okay. So actually 39% of you, which is sort of the majority opinion here, were saying that it's C, and that's sort of what I was looking for. If there's any comments on that, but basically what I'm saying here is the difference is the amplitude, right? So this is this pulse, pulse B has a larger amplitude, I guess. But the point of this is that just that wave speed does not depend on amplitude. It also doesn't depend on frequency, how fast you shake it. All it depends on is what the tension is in the string. It does not depend on amplitude. In fact, we introduced an equation for this last time, didn't we? Which was that V is equal to the square root of F over mu. Oh yeah, it depends on, so F is the tension. As I said, it also depends on what's called the mass density of the string. So if you have a thicker string, like, or made of a heavier material, then waves do travel slower in that as well. So I have a little example here. You have an 80-kilogram climber hanging from a rope. Let's try to draw it here. Maybe like this. There's the climber. M equals 80 kg. 20 meters below a rocky overhang. So this distance is 20 meters. The rope has a linear density of mu equals 37 times 10 to the minus 3 kilograms per meter. I like to convert that into SI units right off the bat. It said grams per meter. How long would it take a transverse wave pulse to travel the length of the rope from the climber to the overhang? So what they do is they send a pulse, wave pulse, and you're trying to find t equals question mark. So if the system is the climber, then the force diagram for that is going to look like there's tension of the rope on the climber acting up, and the force of Earth on the climber acting down, gravity, right? And so what this would mean is that the sum, if you define plus y equals up, then the sum of forces in the y direction, which is equal to 0, is the tension minus mg. So what this means is the tension equals mg. So that's sort of equilibrium there. So let's call this this F, I guess, equals mg for tension. And then I'm going to say that the wave speed, V, is equal to the square root of F over mu. And so assume, I'll put it down here, assume constant speed. Okay, so for constant speed, you've got V is equal to D over T. So T is equal to the distance divided by the speed. So it's going to be equal to the distance times the square root of mu divided by mg in this case. So T is equal to 20 meters times the square root of 37 times 10 to the minus 3 divided by, forgot about the mu. Mg. Sorry, M is 80 kilograms and then 9.8. I'm plugging it all in. I got 0.14 seconds. Okay. Note, we neglected the mass of the rope here. So in reality, the rope has a mass. It has a mass density, right? So you can figure that out. M rope is equal to 20 meters times this 37 times 10 to the minus 3 kilograms per meter, right? So if we add that up or multiply that out, you've got 0.037 times 20. This is the rope weighs about 0.7 kilograms. So this is a lot less than 20, I guess. Okay. Any questions? We got Faison, how's it going?
Good, Professor. I was just wondering, we assumed constant speed. What factors would prevent the speed from being constant?
Well, this factor exactly. So if you don't neglect the mass of the rope, then at any point along the rope, the tension above is supporting all of the weight underneath it. So the system, you would define the system, if you were halfway up the rope, to be the rope that's below plus the climber. And so, and that would all have a certain mass depending on how far you are. And the tension at that point would have to support everything that's below it. So what would happen is that the tension at the top would be enough to support 20.7 kilograms, and the tension at the bottom would be enough to support 20 kilograms. And so the tension would decrease as you go down. So if you're sending a pulse downwards, for example, it would decelerate as it went down. But we're just neglecting that for this question. Sorry, 80 kilograms, sorry. So it'd be 80.7, sorry, good point. Somebody just pointed out that I'm talking about 20 meters. Sorry, what I mean is 80 kilograms. This is much less than 80 kilograms. And so, right, the tension would be at the top would be due to 80.7, so slightly more, and at the bottom, just 80. I still think it would be 0.14 seconds, though, since it's negligible. Thank you, Mia. Okay, good job. So let's go on here. Yeah, I wanted to do some demos. So we're going to stop the share here and show a couple of quick things. And again, this filter is so bloody weird. Let's turn it around. So this is a wave machine, and what this is a bunch of parallel metal rods, and they're connected by a metal spine up the middle. So if I take one of these and lift it up, it sort of twists and sends a wave pulse along at a particular speed. So that's one thing I can do, is send a pulse. I could send 2 pulses. If I send a plus and then another one, and you can see them kind of interfering. They pass right through each other, so that's kind of fun. I can also try to send maybe an oscillating wave, and then you get sort of this standing wave. So that's kind of fun as well. And then the other one that I want to do is I have on the floor there a rubber hose. If I take the rubber hose and stretch it way out, then I can send a wave pulse on the hose. So I can send an upward pulse. You can see it bouncing back and forth. And it's actually tied to a table up at the front. So if I send a positive pulse, I should get a negative reflection. I don't know if you can see that, but the pulse that went that way towards you was positive, and the one that came back was negative. You can try it the other way around. You send a negative pulse, and then I get a positive reflection. And then I can, of course, do standing waves. So this is the fundamental frequency. I can try to do second harmonic with a node in the middle. What else can I do? Let's see if I can do more. There's 1, 2, 3, 4. This is the 4th harmonic. Whoa! So that's the demo. Okay. Good. All right. Share. Hope that looked all right with the weird filter. Yeah, sorry about the. I see. Duncan is saying that the Snapchat filter is kind of decreasing the video quality, so that's not too good. Okay. Ethan, did you want to unmute?
Oh, I'm just want to inform you about the video quality, but you already addressed it.
Yeah. It's too late now. Yeah, maybe I should have turned it off during the demo. Okay. Okay. I want to talk about the properties of sinusoidal waves a little bit. So we talked about wavelength lambda, which is the distance over which a wave repeats in space. This is actual a snapshot. And the period is the time to complete an oscillation of the wave at some fixed position. So as the wave passes by, it'll go up and down. So if you make a history graph now, these are both, I guess, y versus t. Then, so y versus x snapshot and y versus t, that's the history. Then the distance between peaks on the history graph is called the period. The frequency is 1 over the period, and the amplitude is the maximum value of the wave disturbance away from the equilibrium. Okay. And then wave speed is the rate at which the wave pattern propagates. Okay. So, and it turns out that wave speed, wavelength, and period and frequency, they're related by these equations. V is lambda over T, and it's also equal to lambda multiplied times F. So I've got a few little quick poll questions in which we're going to compare two different waves and compare some property of them. Okay, so let's go to quick poll. Here are two snapshots, so y versus x, of two waves that have the same speed. Which of these two waves has the greater amplitude? And I guess C would be if you think they have the same. And let's end the polling here. Right, so this one has a greater amplitude. If you look at this distance versus this distance, I think this looks to be about half, right? Dima Axa, yes, C would be the same. Dima asked a good question. So speed depends on frequency. So not really. So speed does equal lambda times f, but so yeah, if you had a particular wavelength, a fixed wavelength for some reason, and you increased the frequency but kept the wavelength the same, you'd have to increase the speed. But really, the speed is determined by the properties of the medium, right? So what this, it's sort of better to look at this as saying that the wavelength is determined by the frequency, because as the frequency goes up, the wavelength goes down. Because V is usually the constant in this relation. Makes sense? Let's go to another quick poll here. Which of these two waves has the greater wavelength? Okay, and 3 seconds. And in polling. Yeah, you guys got this one. Because the wavelength is the distance between the peaks, the two adjacent crests on a snapshot graph. Let's go to the next one. Which of these two waves has the greater period? Okay, so let's end that polling. So most people were saying B, and that's actually the answer that I liked as well. A little trickier though. we say that they had the same speed. And if we solve out this equation for period, we get that period is equal to lambda divided by v. So this one clearly has a greater lambda. So if lambda goes up, this means that the period also goes up if you have the same speed wave. It's lambda divided by v. And then let's relaunch this one. Which of these two has the greater frequency? Okay, great. Okay, good. Sharing it here. I've got 98% are saying yes. Yeah, so this is exactly it. So this one has you got it. So frequency is equal to 1 over t. So as the period goes up, the frequency goes down. Okay, so you guys got it. All right. So those are sort of general properties of waves. The next thing I want to talk about is wave intensity. So if I'm a speaker, or if I buy a speaker which produces sound has a certain power in watts. There's two things: how much power it actually uses, and that includes creating heat, but also, more importantly, how much power is put into the sound waves, which will then spread out into the world. So watts is joules per second, amount of energy produced per second. And then we can think of these wave fronts, or spheres or hemispheres, each with a certain surface area in meters squared as it spreads out. And intensity is power divided by area. So the intensity of a wave is the average power that it carries per unit area. If the wave spreads out uniformly in all directions and no energy is absorbed anywhere, then the intensity at any distance from a wave source is inversely proportional to r squared, where r is the distance. So at some distance r1, you'll have some intensity I1. If you go to double the distance, then the intensity will drop by a factor of 4, because that same power is now spread over a surface area that's 4 times as large. And the reason that sound intensity is so important is that that's what you actually hear. Our eardrum has a certain area, which is what catches a certain amount of power, and that is fixed. It's about, I don't know, maybe about 1 square centimeter of an opening there. And only the sound that falls on that 1 square centimeter hole in your ear can get into your ear and you can actually hear it. So it is the sound intensity which determines how loud a sound is that you hear. And that's why a further away sound sounds quieter to us, not because it has less power, but because that same power is now spread over a larger area, and so you're only picking up a smaller fraction of it the farther you get away. Makes sense? This is showing if you have a source that's very far away. This is sort of maybe a source as out here at infinity. Then these wave fronts come along as planes. And so the area here doesn't change with time. A is, I call it cross-sectional area. Because if you have V going this way, it's the area which is perpendicular to the direction that the waves travel. And so in a plane wave, this intensity remains constant. In a spherical wave, it spreads out. So in both cases, the intensity is power divided by cross-sectional area. In the case of a plane wave, that doesn't change as the area just stays the same, but it is what it is. In the case of a spherical wave that's spreading out from a point source, then the area is 4 pi r squared. It's the area of a circle which is centered on the source. Annie is asking when would you actually get plane waves? Well, I guess if you had a big source that was itself a plane, I don't know, like a bunch of speakers, and they're all together, like operating together, kind of big field full of speakers, then you'd get plane waves kind of from that. The way it often happens in practice is that you get things that are approximately plane waves if you're far enough away from the source. So if you're very far away from the source, then the spheres can be approximated, I guess, as planes. So what is going on here? Well, what's really going on is that the pressure is going up and down in this kind of wave, and that's propagating along at some speed. This is a longitudinal wave. Sound waves are longitudinal mechanical waves that propagate through gases, liquids, and solids. So in this region, the molecules are closer together, and that makes the pressure higher. And in this region, you've got a rarefaction. The particles are farther apart. So rarefied gas and pressurized gas. So sound waves actually involve small changes in pressure. So P0 might be, well, it's 100,000 pascals. You can go a little above and a little below that pressure, and that's what we hear as being sound. And the higher the amplitude of the sound wave, the louder it is, the more intensity there is. So this, if you look at volume, this is a low intensity sound wave. Okay, it's a little hard to see, but it's pressure versus time. And this is a high intensity. It's actually the same wave, but what we've done is we've turned up the volume. So by turning up the volume, you turn up the variations in pressure versus time. And what is fixed is the middle. So the middle is actually just the 0 point of pressure is what's called the ambient air pressure. And that's just fixed by the pressure of your environment. In our case, it's fixed by the weight of the atmosphere pushing down. And so a crest on this means that the pressure at that time and that place, at that microphone, is a little higher than the ambient room pressure. And a trough means that the pressure is a little lower at that place than the ambient room pressure. I'm responding to some of the questions coming through in the chat, which are great. Someone asked, why do higher pitched sounds sound louder? That's a good question. So I haven't mentioned frequency here. This has nothing to do with frequency. This has to do with amplitude. But you're right. It seems like when you increase the frequency, it sort of sounds louder. That could be due to the fact that your ears are more sensitive to higher frequency sounds. But really, it shouldn't, right? It should be that the amplitude of the sound wave is what determines how loud it is, and the frequency is what determines the pitch of the sound. So a low frequency would sound like this. A higher frequency would sound like this, right? So there's two different things. Whereas a large amplitude sounds like this, and a low amplitude sounds like this. So there's two things going on. That's a good point. Okay, next, what time is it here? 11:38. Okay, we're a little behind, but that's okay. Sound intensity level. The decibel, abbreviated dB, is the unit used to measure the sound intensity level. So there's a team-up quiz, which you can find. We're going to be doing that soon, which is all about decibels. So let's go over them first, and then we'll do the quiz. The decibel scale is a little strange. There's not much physics to it, but it's based on the fact that our ears are incredibly sensitive. Your ears can hear everything from your fingertip brushing lightly over your skin to a loud jet engine. And in terms of intensity, the sound of a jet engine is about 1 times 10 to the 3, 6, 9, 10 to the 12. So 1 trillion times more powerful than the smallest audible sound. That's a big difference. So intensity turns out to be just kind of an awkward quantity to deal with. So what we do is we've defined this new system, which you may or may not like, which is called the decibel system. So if you have a sound with intensity I in watts per meter squared, the sound intensity level is 10 times the logarithm of I divided by I0. We call the unit for beta decibels. So whenever we compute this number, we call it decibels. And in this equation, I0 is a reference intensity, which is 10 to the minus 12 watts per meter squared. This is also sometimes called the threshold of hearing. So corresponds to the quietest sound, 0 decibels we can hear. Okay. Logarithm of 1 is 0, so this would be 0 decibels. I don't know if you have log on your calculator, but if you try log 1, you should get 0. Okay, so that's 0. A sound 10 times more powerful, if you do a logarithm of 10, you get 1. And then you times it by 10, because that equation, you get 10 decibels. If you have a sound that's 100 times more, I guess, powerful, more power or more intensity than the near total silence, then that would be logarithm of 100 is 2 times 10 is 20. So that's 20 decibels. 1,000 times is 30 decibels, etc. So what's going on here is that for every, there's our equation. For every multiplicative factor in 10, you get an additive of 10 decibels. And here I've actually expressed things in milliwatts per meter squared. So this is the quietest sounds. So this is get louder going up the scale here. So the quietest sound is threshold of hearing, 0 decibels, which is 10 to the minus 12 watts per meter squared. I should maybe point that out, minus 12 watts per meter squared. I don't know why I put this in milliwatts per, sorry about that. But the point is, every time you multiply the intensity by a factor of 10, you just plus off 10 decibels. It's log base 10, not log base E. It's not the lun on my calculator, it's the log 10. Okay. And Faison points out that a corridor, or like a column of air, can produce plane waves as well. It's a really good point. So you guys ready for this team up quiz? Hopefully you can place a call to your friends. Oh, this, after the team up quiz, we'll have a vote. You guys know what that's all about. But you're gonna do 3 multiple choice questions on this decibel stuff. Your pod team will share the mark. You need a driver. So you have to go place a call, elect a driver. All the students should log into Quarkus and click on the Team Up Quiz Chapter 11 in Module 6, which should be near the top. You click Go to Tool and then create a group. The driver creates a group. And then the driver tells everyone in the Microsoft Team window what the session ID is. And then once all the non-drivers get the session ID, they also join the Team Up Quiz, and you should see all of each other in the Team Up Quiz. And then you start with the questions. Once everyone in your room arrives in Team Up, please achieve consensus before the driver submits the work. So I'm going to go on mute for 10 minutes here. I'm going to go over to the Physics 131 Help Center, which is a different Zoom call, and see if anybody who doesn't have a Microsoft Teams group wants to team up over there. And so 1 more minute, please. There were a couple of people reporting that in their team up quiz, there were people that they didn't invite. So that is a little strange. Not sure how that worked exactly. But what I want to do, hopefully you've finished the questions, and let's go over them now. But before we go over them, why don't we have a quick vote on this television program thing. So if you're back, I'll relaunch here. Just do a 15-second quick poll here, and then I'll talk about the results of the team up. People voting E here. It's fine. Okay. And so, woo! Yeah, 61%. But there's also a lot of people, 33%, or fans of. Good Place, which is also pretty good show. Okay, so this is about intensity, and the idea with intensity is actual energy. So intensity in watts per meter squared is the energy. It's the physical quantity. So 10 singers, as long as there's no weird interference, should produce 10 times the energy per second. Does that sort of make sense? A there per area, if they're all the same distance. And then the next one, so this is the same thing. It's 80 decibels. But if you get 10 singers, then what's going on there is you're multiplying by a factor of 10 times I by 10 is U plus beta by 10. So it goes from 80 decibels to 90 decibels. Now this one, when you turn up the volume on your earbuds, the sound originally entering your ears at 50 decibels goes up to 80 decibels. That can happen if you go from 5 to 8. This is, so 50 to 80 is 3, the way I do it without even logarithms, is 3 steps of plus 10. So this corresponds to 3 factors of 10 in intensity. Okay, 10 times 10 times 10 equals 1,000. It's 1,000 times more intense. So we're going for there. What's the time? 11:57. Well, I don't have a lot of time. I think what I want to do is quickly go over a little bit about the principle of superposition, and then we'll on Monday we'll return to this. Let's just go through this. So particles and waves. So particles cannot occupy the same space. And here's a guy on his motorcycle trying to see if his motorcycle will occupy the same space as a brick wall. And the answer is no. But waves are not like this. They pass right through each other. They interfere. So here's a wave from the left and a wave to the right. They come together and they just pass right through each other. And what's being shown here is the black line is the actual string, so the actual disturbance of the wave. The dashed red line is representing the wave that goes from right to left only. And the dashed blue line is the wave that's going from left to right only. And so you can see them come just when the waves are interfering, and the black line is just the sum of those two. So that's called the superposition principle. If 2 or more waves combine at a given point, the resulting disturbance is the sum of the disturbances of the individual waves. This is called wave interference. And this, this has the result that you can have constructive or destructive interference. So for example, if you have two speakers and they're both playing one sine wave at one particular frequency, if you adjust them so that all the crests are right on top of each other, then you'll get a wave that has twice the amplitude. But if you do it like this and you set it up so that one speaker, so that the wave from one speaker, all the crests are at the places where all the troughs are from the other speaker, it turns out the principle of superposition just gives zero, okay, the equilibrium. So you just have zero pressure, not zero pressure, you would have the ambient pressure, whatever the pressure in the room is, it would be a quiet room with just the background pressure and no extra up and down. I think that's pretty much all I've got time for today. I want to talk about standing waves. I think I overplanned a little bit, so I'll do that next time. We have some time for sure on Monday and even on Wednesday. We've got 3 lectures next week. So what's going on next week is there's 3 classes, but all we have to do is finish chapter 11. So this is what the plan was for chapter 11 for Monday, 11.7 to 11.9, so standing waves, beats. Wednesday, I wanted to talk about Doppler effect and kind of do a little course review. So if we're a little behind, we'll finish it up chapter 11 on Wednesday for sure. And then Thursday, it's just more kind of course review. We're going to do that bonus team up quiz. I've got some demonstrations that were with liquid nitrogen where I'm going to be putting some superconductors on and cooling them and seeing if they can float, that kind of stuff. And one good thing to know, which I just learned today from you guys, is that if you're using a snap filter, you should turn it off for the demos so that you can actually see the video a little better. Let's see. And there's no Friday lecture. It means Thursday. So it's a good point, Chang, is that Wednesday is the last day of classes, and Thursday is what's called Wacky Thursday. It's a makeup class for Thanksgiving. So anybody who missed a class like we did on Monday in October, then the makeup day is Thursday. Okay, I'm going to turn off the record and then go to the hands.